What we're going to do today is we're going to go through section 10.1, and then after that what we're going to do is we're going to begin the next section, which is a combination of 10.2 and 10.4. Okay? So we're going to do a little bit of both today. In the next class, which is tomorrow, we're going to take a look at section 10.2 and 10.4 again, finish it, and then do section 10.3. So really what we're doing is we're doing like 3 lessons in 2 days. The lessons are mainly conceptual. There's not much math involved here. The math that's involved in today's section is the easiest math you will ever see in physics. It's converting temperatures, right? I mean, that's really simple. And you're given the formula, so you don't have to memorize it either. Then on Thursday, we're going to review, and then on Friday is your test on chapters 9 and 10. Chapter 10 is mainly conceptual. The mathematical, God bless you, stuff is very easy. Chapter 9 is mainly mathematical, but obviously still with conceptual stuff. If you were not here on Friday, you need to make sure that you take a look at that video, or at the minimum, look at the problems under documents and handouts listed chapter 9, math review or something, and the solutions are there as well. Okay, you can look at both of those.
What if you're taking the AP English test tomorrow?
If you're taking the AP English test tomorrow, what I want you to do, obviously, is to watch the remainder of the video from 10.2, 10.4, and watch 10.3 tomorrow. Just because we're reviewing on Thursday. So, if you're taking the exam, you have the morning, but then you have the whole afternoon off. The recordings, if you watch my versions, will only take you like 20, 30 minutes. Okay? So you still have to do that. Whenever you're out for an AP exam, you're responsible for the work that you miss. Okay, that's when you get into the AP tests. It's tough, but you have to do it. So at least you guys have the videos to look at. But I recommend doing it tomorrow, not waiting until Thursday, because Thursday we're going to review. And if you come in on Thursday and have no idea for the review, you're going to feel lost. So spend the time tomorrow doing it. Or feel free to go ahead tonight, right, if you want to, and watch the rest of 10.2, 10.4, and then watch the 10.3 video tonight. You can look at my videos that I've already recorded because they're shorter, if that helps you. Okay? I'll put all those notes up, my version of them tonight as well. So in 10.1, we're going to talk about temperature and kinetic energy, thermal equilibrium scales. First, the definition of temperature. As you already know, whether it's from physical science, chemistry, maybe even biology, but the temperature is a measurement of the kinetic energy of the particles in a substance. So, the easiest way to think about this is thinking about when you heat up some sort of a fluid in a closed container. It'll start to want to evaporate and move. Particles will get moving faster. What do you notice what happens when you boil water with the lid on? Eventually what happens to the lid of it? Yeah, it starts to like bubble and shake, right? Because you're building up pressure inside there, one, and the temperature is increasing, causing the particles to move faster and faster and faster, causing gas to be created. That gas is then moving around, and you have steam and that pressure, which causes the top to move. But the concept is that if you have no motion of the particles, you have no temperature. So we're going to talk about that today, what that indicates about the temperature of a substance if there's no motion in the particles. Okay, so the average kinetic energy of the particles is considered to be the temperature of a substance. Now, what happens if we add and remove energy here? So simply put, when you're adding energy here, what you're literally doing here by adding energy to the system is increasing the temperature. Okay, as energy goes up, temperature goes up. And specifically, it's the kinetic energy of the molecules that are measured for temperature. But generally speaking, as you add energy, you're adding temperature. How can you add energy to something? What are some ways you can add energy? You could just simply add heat to the substance. That's one way to do it. Good. What else? You can either add heat to the substance to add energy, or do what? Get the substance to what? What am I doing in my hands? Yeah, flow or move. Okay, as you add energy to something, its temperature will naturally increase. Now, specifically here, we're talking about adding thermal energy though. Okay, thermal energy is what we're really looking at here. So as you increase the thermal energy, you add thermal energy, add temperature. In chemistry class or at home, you have 2 ways usually of doing it. Electrical heating, which is conduction. You put the pan right on the coil, and the coil heats it up. We'll talk about conduction later today. Or heating by using a gas, which is a combination of conduction and convection. variation as well, actually, too. But we're not specifically looking at that here. Let's talk about temperature as a relative term. Okay, a relative term. Why is a glass of ice water in the summer considered quote-unquote cold? Why is it cold? Why would you say when you pick up a glass of ice water, all that condensation is on the outside, why would you say, ooh, this is cold? Why? Yeah, it's relative to the temperature around it. In the summertime, it's usually pretty hot. So that ice cold water feels very cold, doesn't it? And your body is 98.6 degrees. So if you want to cool down, you drink ice water, which might be around like 40 degrees, and you're having your body, by the nature of thermal equilibrium, begin to cool down when you drink cold water. You would never drink hot chocolate in the summer. It doesn't make sense, right? Now, in the winter, hot chocolate feels hot because obviously around you it's pretty cold, right? And you yourself can be cold in the wintertime. And hot chocolate could be up to like 180 degrees Fahrenheit. Your body's only 98. So now you're warming up your body by drinking hot cocoa, or hot chocolate, whatever you want to call it. So it's a relative term. For example, what if there was an alien race that lived in another galaxy and their body temperatures usually operated at like 220 degrees Fahrenheit, 220 Fahrenheit, and you give them a cup of hot chocolate and it's 180 degrees Fahrenheit. To us, it'd be hot. What about to them?
Cold.
Yeah, it'd be colder. Maybe not necessarily ice cold. Well, ice cold is a term. We know ice isn't substance ice. But maybe not very cold, but colder than their body temperature of 212 or 220.
Is there like a certain temperature that like burns you, like for your tongue? I mean, your tongue, for example, like something's gonna be really hot now versus it doesn't have to be something hotter.
I don't think there's an actual numerical value, but I guarantee you there's like probably a range of values at which most people would start to become burned. And that's when you look at like first degree, second degree, third degree burns. Usually the temperature of the thing that burns you and the length of time it's on you for indicates the first or second degree or third degree burn. I don't know. I mean, if you take boiling water literally off the stove and drink it, doesn't matter how much you can withstand, you're going to burn your throat. So I would assume 212 and higher will burn you, but I don't know what range there is. There's probably a range between like 180 and 1 or 200. That's like, it might burn yourself, you might not. Below 180, maybe it's like not even hot anymore. But there's probably a way, I mean, you could test it, but that'd be a terrible test to run, wouldn't it? It'd be a really terrible test to run. For an opportunity for a simple extra credit for you for this section. This will go on your next test if you want to do it. I told the other class, it's very simple. Get 3 bowls of water. One of the bowls of water, you want to be ice water. So fill the bowl with ice, then put water in it. Allow for enough for you to stick your hand in it though. Don't fill it completely with ice, but you want it to be ice water. Stir it for a while so it cools down. So it's really, really cold. Fill another bucket of water, or like a bowl of water, with hot water. Not boiling hot, but hot enough that it's hot. Hot water that you would fill like a bathtub with, okay? Take one hand in the hot water, one hand in the ice cold water. Hold them there for at least 30 seconds. So if it's too hot for 30 seconds, it's too hot, okay? Don't burn yourself. So 30 seconds. Then, in between those 2 bowls of water, put a bowl of water at room temperature. Right? You need to do room temperature. You need to either figure out that it's room temperature or just leave water out for a while. Take your tap water, put it on cold, or put it maybe in between the middle. Run it for a little while. Let it sit for like an hour. That's definitely room temperature then. Take your hands out after 30 seconds. Put them directly in the room temperature water. Directly in. And then describe in the video what you feel. Okay, it's kind of cool actually. I think, it works well if you hold your hands in the other water for long enough. Some people will put it in for like 10 seconds and then do it. You don't feel the same sensation you should. If you do it the right way, if it's cold enough and hot enough, and you hold it for at least 30 seconds and do it, you'll notice. If you really don't notice, you want to do like for a minute, you can. But put them both into the room temperature water. But make the room temperature water bowl big enough that your hands aren't touching. Okay? So don't put them in and have your hands touching, or else it'll ruin the effect. Have them separate in that middle bowl. And then just describe in the video what you notice. Okay, and it'll be related to this topic, this slide of relative. All right, now thermal equilibrium. Thermal equilibrium. What do you suspect thermal equilibrium means? I mean, we see the obviously definition here, but how is it related to where we've heard equilibrium before? Give me an analogy to equilibrium from earlier in the year. We have not done thermal equilibrium, we've done another type of equilibrium in the past.
When like the forces are equal.
Yeah, when the forces are out of balance or equal. So it's the same idea here. Okay, when two objects in contact are at the same temperature. For example, take your hands, put them together, as if you're praying or as if you're about to bow to somebody. They're about the same temperature, right? You don't notice much difference. Both hands are about the same. Okay, now take both of your hands, put them on your desk. The desk is not very cold, but it does feel cold in your hands, all right? Because your desk is at the room temperature right now. Your body's 98, the desk is probably like 70 degrees. So naturally it feels cold. So this goes back to the previous slide with the relative nature, right? But it's also about thermal equilibrium. Hold your hand here for long enough. Hold it there for 30 seconds. Take the other hand off if you want. After about 30 seconds or so, remove the hand on the desk and then touch the desk. You'll feel it's warm. You can feel the warmth with the other hand. What you're doing is you're causing the desk's temperature to come up to the temperature your hand is at via thermal equilibrium. Thermal equilibrium is the idea where two things want to be at the same temperature. You take a can of soda that's in the room, you put it in an ice bath, what does it do eventually? It gets?
Sweat.
You know what? Sweat? Yes, it'll start to sweat on the outside. Take a can of soda though, room temperature. Put it in a cooler. What does it do? It gets cold. Why? What's happening to those two temperatures? The temperature in the ice cooler might be like 36 degrees, right? The can of soda might be at 70 degrees room temperature. So it goes in at 70 in an ice bath of 30. So what's going to happen to the temperature? It's going to eventually... Yeah, it's going to be equal. Maybe the temperature of the ice goes up a little bit. Maybe it's like now 36.2 degrees Fahrenheit. But the temperature in the soda gets all the way down to 36.2 and they reach equilibrium. Okay, they reach thermal equilibrium. Now, we're going to look at this in a moment, but let's talk also about something called thermal expansion, which is related to equilibrium. This example here involves thermal equilibrium and expansion. What do you remember from chemistry about thermal expansion? What do you remember, generally speaking, not about water or H2O, but generally speaking?
As a substance heats up, it usually expands.
Yeah. As a substance gains in temperature, it usually expands, and as it decreases in temperature, it usually contracts. Okay, so we have an example here that's very applicable, an old school mercury thermometer. In the bottom of the thermometer, known as the bulb of the thermometer, there's a lot of fluid. That fluid, when heated up, starts to expand. The expansion of that fluid rises up a thin tube. The thinness of the tube is what allows it to increase in volume enough that it's significant that you could see it. So when you increase the actual temperature, you're increasing the actual volume, causing it to rise in the thermometer. Okay, this is an example with mercury. What are thermometers made of now? Anyone know? I honestly forget. Is it iodine or something else? Anyone know? What is it? Is there an alcohol compound? It might be actually. I don't think it's iodine because iodine I think is purple and it's like a red. Okay, just curious. I don't remember.
Because there are some of them that do air pressure and then some of them what? So the ones with air pressure.
Yeah.
There are ones that
A barometer?
Yeah.
A barometer measures air pressure.
Yeah, but there are other ones that are like that, I think. At least my friend has one.
That it measures temperature, but it uses air pressure to help measure
Or
temperature?
something, yeah.
Okay. Mercury? Yeah, the old school ones were always mercury, but mercury's been banned now because it would break in the lab, and if it breaks and gets on you, it can become
It's just poison.
toxic, poisonous, yeah. Okay. Where else do you see thermal expansion? Think about the seasons. Think about the seasons in the year. Where's an example of thermal expansion as the seasons change? Or thermal contraction, obviously, of expansion.
In the ground, the sidewalk cracks if it gets too hot.
Yeah. In the summertime, the road expands a lot. So there's a lot of cracks in the road. And in the winter, it contracts. So you get a lot of potholes in the road when the concrete or the asphalt contracts. So sidewalks are made in a certain way. What do you notice about a sidewalk? It's not a continuous layer of pavement. What is it? Yeah, the slabs. What's between those slabs usually? Some crack and spacing. That spacing is usually made of material that can easily that is very malleable. Malleable meaning it can change its shape and volume easily. So it's like a material like caulking in a window that you would put to insulate a window, that foam material you put around a windowsill or a window frame, that's easily contractible and expandable because of its material properties. So what else? What are some other examples? There's other stuff besides that. That's a really good one though. So we talk about the roadways and sidewalks. How about a bridge? Ever go over a bridge? What do you notice the bridge is made into again? What is it? Sections. And in each section, ever look at a bridge? You're going to see teeth. Next time you're going over a bridge, if you're not driving, try to look out the window and look at the bridge. You'll see teeth joining at each section. Why? What does that allow for? Yeah, it allows for movement. So when there's expansion, the teeth just get closer. When there's contraction, the teeth get further apart. But they can easily move. Okay, similar, ever get off the 456 train at Union Square, and they have the moving platform that extends off the train so you don't like miss the gap and fall through? How those teeth move? Believe it or not, on a bridge, same idea. They can easily move back and forth like that. How about in the wintertime? You guys don't know this now. Well, some of you might know it if you have a permit. What happens to your tires in the wintertime?
The air pressure goes, they get like flat.
Yeah, they get flat, they deflate, I was hearing. The air pressure goes down. Now, most cars nowadays that are newer cars in dealerships that have this fill their tires with not oxygen anymore, but a nitrogen-oxygen compound. Nitrogen does not contract as much as oxygen. So in the wintertime, you don't actually have to top off your tires anymore. But most people, if you know this, if you've been driving for years, in the beginning, well, when it starts to get cold, you top off your tires with a lot of air. If it says to fill it to 32 psi, you do it to like 34 in the winter. Okay, because in the next week or two, it's going to deflate itself naturally. Okay, you don't go too high or else what will happen will pop. Okay. What else? In the summertime, one more example I could think of that I wrote down.
I mean, mine's more about fitting a ring on a finger.
Okay.
And how in the summertime it's harder to put a ring on a finger because your body expands, but in the winter the ring falls off because you're older.
Yeah, your body naturally expands and contracts also. Your feet and your hands can get bloated at different times in the year and based on what you eat. Anybody ever know when you eat a lot of salt, it causes your toes and your hands to kind of bloat a little bit. That's one of the other things that cause that, but temperature also. Yeah, I know, it's the weirdest thing. My mom used to always tell me that's why she didn't eat a lot of salt, she would say. But I don't know if it's actually true or she just made it up, but I'm assuming my mom was right. I mean, you could look it up, but don't tell me if she's wrong. I'm making believe she is. But temperature definitely affects it in the summertime. How about a door in the summertime? Ever try to open a wooden door in the summertime? It sticks. You hear it and you're hot. Well, it's because the wood is swelling in the summer. It's expanding. Okay? Thermal expansion is responsible for a lot of
in the
issues.
winter or the summer?
Summer. Because the temperature increases, volume increases.
Yeah, the winter, my hands get really swollen when they're cold.
Do they?
Yeah, like really swollen.
Your mother was right, it increases your water weight.
Is that what it is? I don't know. That's interesting. I wonder. Maybe it's just getting sore, so it feels like it's throbbing. Like I don't have arthritis, but they get very in the winter they get very cold. Do they?
Yeah.
Really? Maybe because there's some fluid like water in your body, and the water contracts in the winter. It's the opposite action.
I think I have poor circulation.
Well, let me think. Yeah, H2O forming ice expands. Maybe because your body's made up of mainly water, a lot of water, it's actually expanding in the wintertime. It's not freezing though, so it wouldn't, form ice. Okay, let's take a look at some common temperature scales. These are ones you definitely know of.
You never put a jar of hot water?
If you want to open a jar, that's another really good one. If you want to open a jar of sauce or pickles that's been vacuum sealed, run under hot water, it's much easier to open it up. The lid will expand, it will be easier to take off. The metal lid. The glass itself will not expand as much.
Maybe the opposite if you run it under cold water.
Yeah. If you run it under cold water, it will contract. Not a lot, but enough to make it significant when you're trying to open it. Remember, a glass jar under hot water is not going to expand much, but the little cap is metal. The metal will expand, causing it to be easier to open. It's looser.
break if you have cold glass and you put it in hot water?
Certain things has to do with the tempering. So certain materials that are not plastic, that are actual glass, that are like a lattice structure, when the change in temperature occurs in too big of a time period, the molecules try to rearrange themselves and they have a shattering effect. It weakens the structure strength. I learned a lot about that in materials science and engineering. So it's a good class to take if you're going to go into any engineering. It has to do with looking at like molecules at a molecular level, or chemistry if you're going to study chemistry too. So temperature scales, let's take a look at. What's the freezing temperature we know of? What do we use in the US? 32 Fahrenheit. What is it in other countries? Zero. Make sense of that real quick. Look at the scale. Plug in 0 for Celsius right here where I'm pointing, please. Plug in 0. What do you get? 32. Okay, again, plug in a 0 here. This becomes 0 plus 32. So Fahrenheit is clearly 32. Plug in the 32 from Fahrenheit, though, down here. What's 32 minus 32? So you prove that it is 0 for this one. Okay, that's where the 32 comes into play. You don't have to memorize these, but easily convert. Okay, easy. Let's look at absolute temperature scales. In chemistry, you probably use this with Kelvin when you used PV equals nRT, or PV over T equals PV over T. Was that Boyle's gas law? No, yes, maybe so, I don't know. Okay, well, absolute scales are extremely, extremely useful when it comes to being a physicist or engineer or scientist. A lot of the time, the laws of conduction, convection, and radiation pertain to Kelvin. They don't pertain to Celsius, although Celsius is our base metric system to use. We use Kelvin a lot for our laws because they're based off of the Kelvin scale. Now, what does absolute zero actually mean? What does absolute zero actually mean? I mean, you can feel free to read, obviously, on the board. And maybe a follow-up question to think about while you're answering. Why can we not get to absolute zero? What does it mean, and why can't we actually get there?
Because there's nothing moving, that's impossible.
There's nothing moving. There's no molecular motion whatsoever. That's what absolute zero is. Why can't we get there?
It's impossible. Like,
Why is it impossible?
You can't make molecules stop moving.
Why not?
Because you can't create a perfect environment by like completely changing the environment. You can't create like. Doesn't that make sense?
Yeah, there's always some sort of heat flux going from one thing to another. That's one way to think about it. There's an easier way to do it. There's an easier way to think about it. That does work, but there's a way to think about it that involves limits and the idea of calculus a little bit, actually.
Isn't it like, it takes a lot of work? It takes like a lot of work to get to absolute zero. So like the amount of like work you need to put in, like, it doesn't make sense.
But it doesn't still tell me why you can't get there. That's just saying it's not reasonable, right? What Paul's saying is, you're right. It would take a ton of energy to run an air conditioning unit to cool something even near the temperature of absolute zero. So it's not useful, it's not reasonable. But why can't you actually get there is the question. It's a very conceptual, theoretical idea. I'll go to Kira then back.
Is the thing that like if nothing can move in that environment, so even if you did it, this can't.
No, nothing can move in that environment.
Move the molecules just like fall apart.
It's not even like more scientific, it's more mathematic, actually. Mathematical. How do you, I'm going to give you a hint, and I guarantee you some of you will get it. How do you cool down a can of soda? What do you do?
Oh, because
Fridge.
So say it again. Put it in something cooler. So as a result, there's nothing cooler than absolute zero. So how could you get something down to absolute zero? Think about it. The only way to make something cooler is to remove heat from it. Right? To remove heat from it into something that's colder than it. Well, you can't get colder than absolute zero, so nothing can remove heat from something that's near absolute zero to get it to absolute zero. It's called a limit. In physics and calculus, you're going to hear a term, the limit. Okay, it's a limit that's approaching a value. The limit is zero. You can get closer and closer and closer to 0 degrees Kelvin, or 0 kelvins, I should say. There's no degrees there, really, which is weird. But you cannot reach it. Okay, you cannot reach it. So that's another side note. Kelvins are not called degrees Kelvins, believe it or not, they're called Kelvins. But Rankine is degrees, Celsius is degrees, Fahrenheit is degrees. It's just named after, very picky about it. Okay, some applications quickly. Fahrenheit for temperature, like meteorology, medicine. In the US, if you go to the doctor, they don't say, what's your body temperature today? Is it this Celsius? No, they say you're 98.7 Fahrenheit or you're 102 Fahrenheit. So you have a fever. It's in Fahrenheit, so medicine. And non-scientific uses. Celsius, medicine in other countries outside the US, and then other sciences internationally. And then, as I told you before, Kelvin for physical chemistry, gas laws, astrophysics, thermodynamics, and other areas in physics. Kelvin is the way to go, really. Okay, you're going to hear everything in Kelvin. Let's look at a quick example. It's very, very, very simple here. The lowest outdoor temperature scale I've recorded is negative 128.6 Fahrenheit in Antarctica in 1983. Figure this out in Celsius, Kelvin, and Rankine. So we're given Fahrenheit. If I'm given Fahrenheit, which formulas can I use to convert? Which of them involve Fahrenheit? Two of them do.
The Celsius formula,
Which equals?
isn't it 5/9 times Fahrenheit, like
The quantity.
minus 32?
Good. The quantity, Fahrenheit minus 32. And then you could also convert from Fahrenheit to, what's the other scale? What could you convert from Fahrenheit to? Look at your other formulas that has Fahrenheit in it. Pat? Rankine. Remember that Rankine is the same as Fahrenheit, it's just 460 more. Again, you're going to be given these, you don't have to know them. Rankine is the absolute scale that corresponds to Fahrenheit. Kelvin is the absolute scale that corresponds to Celsius. So we can do these first. Plugging those values in, I'm going to give them to you for the sake of time. Negative 89.2 degrees Celsius. 331.4 degrees Rankine. Okay, and then once I have Celsius, I could take that number and convert that to Kelvin. Okay, so I'll take this number in Celsius, plug it in down here to give me the degrees in Kelvin. Simple conversions. Okay, got to be able to convert between temperature scales. Really easy stuff. All you're doing is plug and chug. Okay, and I'm not even asking you to memorize. I thought it's not worth it really. Doing is this homework for sure. We're going to start the next section now, but you're not going to do that homework.